Hey there. We are going to continue exploring the ModFlow solvers, and we're going to go back to this same Fremont River problem, but we've made some changes. The hydraulic conductivity has been increased to 1.5 meters per day from 0.1, so that's about an order of magnitude increase. So that should, our pumping rates on the wells, it should make that converge better. But the two wells have been turned off. We don't want to mess with the wells in this case. And then rather than using a flat bottom, we've interpolated a set of bottom elevations from a set of scatter points. And so that gives us a bottom elevation, set of bottom elevations that slope up to the west side. And so once again, there's a startfiles.zip, which you can download and unzip. And I've gone ahead and unzipped that already. And the resulting file is in this thin aquifer folder, so thinaquifer.gpr. And this is what we have. I'm going to expand the Project Explorer window here. And let's see, I'm going to turn that background color to white. And let's zoom in just a little bit. In fact, let's also change our contouring options to be linear plus color fill. So what we're looking at right now are the bottom elevations. So the top elevation is still flat, and if you look down here as I move the cursor, it's still at 400 meters. But the bottom elevations, instead of being a flat, originally they were 250, and then in our last exercise we changed it to 280 to make the aquifer a little bit thinner. But now, over on the right, it's around 300, and then it kind of slopes up to the left. So if you recall, the drains here are only at 3/17, and it slopes all the way up to like 325 over here. So I've purposefully modified this so that we have a really thin aquifer. And the reason I did that is because when you have a thin aquifer and where the water table is not very far above the bottom elevation, it tends to be a ripe environment for things like head overshoot and convergence problems. And so let's see what happens. That's the only change we made. Everything else is the same. Oh, and like I said, we reduced or we eliminated the two wells, so we're not dealing with that. And so let's save and run this, and what happens, as you can immediately see, is we get a whole bunch of dry cells over here on the left. Now, that could be perfectly legitimate. It could be that just given those conditions, the amount of water you have coming in, that part of the aquifer just really should be dry. But again, we need to verify that. So a lot of times when you have cells go dry, it's because it tries to move the head too far as the solver iterates. And so the first thing we're going to try is we are going to, let's see if our starting heads were too low. So our starting heads are around 317. Well, guess what? If you look at the bottom elevations over here are 325. So right off the bat, we know that that's a huge problem, because if your starting heads are below your bottom elevations, again, look at this, 317, and eventually over here it gets below 317. But on the left-hand side, and by the way, I'm looking at this value right down here as I move the cursor, it's about 325 over here, and so that's a problem. So the first thing we're going to do is we're going to change the starting heads to be, let's say, let's say 350 or something like that. Let's try 400. Let's try that, which is the top elevation of our grid. And we'll save and run that and see what happens. So now our band of dry cells is much thinner than it used to be. It used to extend out farther. So that that fixed some of our problems. Um, but did that, should these cells still be dry? Let's see if we have a head overshoot problem at this in this with this set of inputs. And so I'm going to go into the PCG solver. We'll increase the number of iterations. Whenever you reduce the acceleration parameter, it's a good idea to increase the number of iterations. So I'm going to put that down to 0.1. And let's save and run that and see if that, well, maybe we didn't go far enough. Let's try 0.01, make it a really small step that it takes. It should increase our number. Still didn't change our number of iterations much, so that kind of tells me that it's not, the acceleration parameter is not going to get us very far. You know, maybe we just need to move the starting heads to be closer to the bottom elevations. That's the other trick you can use to stop head overshoot problems. So the bottom elevations are around 325. So what if we changed our starting heads to be 330, let's say, so just above those bottom elevations to start with, and we also have a small acceleration parameter still. So at this point, a combination of how about that? So with a combination of a small acceleration parameter, our acceleration parameter is still 0.01, and by moving the starting heads to be just above the bottom elevation, we were able to get a simulation where we don't have any dry cells. So clearly, this was a case of head overshoot. And again, head overshoot is when it moves the heads. You start the iterative solver and it knows that it has to reduce the heads, but it ends up moving it too far. It moves it below the bottom elevation, and once it does that, the cell immediately goes dry and it stops. It doesn't automatically re-wet the cell. Now there's an option in the LPF package to turn on cell re-wetting, but by default that's off, and we were able to solve it using this other technique. And so by taking small steps with the solver, by reducing the acceleration parameter down to 0.01, and by making the starting heads closer to the bottom elevation. In this case, it took a combination of those two things to get this to properly converge on a solution with no dry cells. Again, there are certain cases where the dry cells are legit, but in this case, it was a head overshoot problem. Now, I want to show you something else. I'm going to push the starting heads back up to 400. And let's see, 400. And click OK. And save and run this. So we're going to go back to a condition where we're getting dry cells. We have the head overshoot problem. But again, another way to solve this is to go into the global package and turn on ModFlow NWT, and then select the upstream weighting flow package, which is only available with ModFlow NWT. Excuse me, and it's the NWT solver that we want. You can do either one of these. The NWT solver in combination with upstream weighting. And click OK, and we'll save and run. Converges fairly rapidly, and once again that also gave us a solution. So ModFlow NWT, again, its forte is dealing with cell wetting and drying issues. It's a very robust solver. If you get a dry cell with the ModFlow NWT solver, by golly, you really should have a dry cell as part of your solution. And so that's another tool you can use to deal with this head overshoot problem.